name is Don Parkinson, and I'm a consultation specialist with Atkins Realis. Today, we are continuing our series of live stream topics as our project moves through into consultation round 3 of the environmental assessment phase. The topics we are covering parallel our project activities or are of community importance, so we hope these will help our viewers and listeners better understand the project and provide input along the way. With me today, as usual, is my co-host, Jennifer Ashwazake Pereira, my colleague and an Indigenous engagement and traditional knowledge specialist at Atkins Alice. Jennifer is a member of Henvey Inlet First Nation, which is on the French River, south of Sudbury, and works with me on our projects across Canada. Hi, Jen. How are you today?
Anine, good for a Monday.
Yeah, that's right. Yeah, it's a Monday. So
Miss
say no
Jen.
more, Jen. Say no more. It's a Monday. Yeah, that's right. But we got a good topic today. Should be
We
lots of fun.
do.
We're going to talk about the preliminary findings of the groundwater studies. And you and I were just discussing before we came on air about how nice it is to be able to actually talk about the results of all the hard work the teams have been doing
That's
in sort of
it.
trying to establish that baseline, right? So now we get to talk about the results and help everyone understand the results, so they can dig more deeply into the reports and look at all the details. Because again, in our presentations, we don't show all the details. We just
That's
try to
right.
give people an understanding of how to interpret what they
And,
can read if they want to
right.
dive into the reports.
And if
Sorry,
they
what
have
were you
any
going to say?
questions, that if they have any questions when they're diving deeper into those reports, the team is available to answer any questions.
Correct. So this is a bit of a primer, I guess, for everyone is the best way to describe it. Just a sort
Mm-hmm.
of introductory kind of little quick preview into our results. And today we're going to talk about the groundwater work that we've done. Um, but before we do that, let's just do a run through of today's topics. We're going to, as we normally um, do a bit of a project background and to get everybody up to speed on the project. Then we're going to talk about the groundwater studies themselves, preliminary results of the field surveys, and then we're going to talk about how you can, speak your voice and provide input to us. So quite a bit to cover, and let's kick things off with that background and just remind people that the project is located in northern Ontario, northwestern Ontario. The road runs from Webequie First Nation, which is about 200 to 250 kilometers from both Hudson Bay and James Bay, and it runs southeast to the McFalls Lake area, which is east of the Mukotai River. So that's sort of where the project sits. It's about 600 kilometers north of Thunder Bay, almost due north, slightly northeast of Thunder Bay. So it's quite far north. Webequie is a remote community as well. And in terms of the purpose of the supply road, three main purposes exist. The first is to move materials, supplies, and people from the airport in Webequie to the McFalls Lake area. The second is to provide employment and economic development opportunities to Webequie while allowing the culture and language to be preserved there and enhanced. And then finally, to provide opportunities to young people, and those would be opportunities when it comes to just work experience or training opportunities, and with the hope of encouraging them to extend their education through post-secondary education or other forms of post-secondary training. The project itself is a planned 107-kilometer two-lane gravel road, as I mentioned, running from Webequie Airport southeast to the McFalls Lake area. 17 kilometers of those 107 kilometers actually sit on the reserve lands. The actual planning corridor width that we're working with, the preferred corridor, is 2 kilometers. So the idea is that the road would sit somewhere within that 2 kilometer wide planning corridor. So we give ourselves some space. So you can imagine a band, land and water, running from Webequie Airport to the southeast to McFalls Lake area. So the actual road would sit somewhere within that 2 kilometer wide band. And the right of way or the cleared area would be 35 meters in width. In terms of other details about the project, remember it's more than just a 2-lane gravel road. There are 3 major water body crossings. The first, as we move out of Webequie, is that of the crossing of Winisk Lake, which is about 200 to 250 meter wide span. And the second is the crossing of the Winiskissis Channel, which is about 30 to 40 meters in width. And then the final major crossing is that of the Mukatai River, which is again 30 to 40 meters in terms of crossing width or span. There are on all these projects both temporary and permanent facilities that beyond just the road itself. Construction camps would be temporary, of course, because they house the construction workers. These would exist at 4 different locations along the route, and they would, of course, accommodate construction crews. And then typically they also include additional lands for storage and laydown of equipment and materials. And so those get incorporated in there. And those camps themselves have their own associated infrastructure, such as like a small wastewater treatment plant, and drinking water storage tanks as well. So that's a bit of back on the project itself. And now we're going to move in to the groundwater studies and talk a little bit about those. Um, Groundwater is also known as spring water by many community members, and it's can be a bit of a mysterious topic. I think for a lot of people, they don't often it's more the water that you see, the surface water that people know more about. But in terms of the studies that are undertaken, they're both desktop and field studies. So we do a lot of review of background information. We look at previous work done in the area, on whether it's on other projects or just initiatives of the province to gather information about existing conditions in the area. And so we look at that information because it allows us to sort of evaluate the baseline data we collect and see whether it makes sense, if it's consistent with what we've we've observed before or what has been observed before, and we'll get into that a little bit later on. And what we're trying to do is, again, as we are with all the other disciplines, Jen, we're just trying to get a snapshot, right, of the way things are. Like, get those existing conditions, understand those existing conditions, because without knowing the way things are now, you can't. It's difficult to be able to sort of anticipate potential effects or impacts, and even to
That's
measure
right.
those if you don't know the way things are now, right? So, um, that's sort of a description of the desktop studies and some of the field studies. And let's continue with the discussion of the field studies and the kinds of things that we did. Um, so we installed 12 what you call monitoring wells, and these monitoring wells are like mini version of a water well, except we're using them only to be able to do 2 things. Not all of them allow us to do one thing, but we're looking at quality of groundwater, and we're looking at um, how how the
How
groundwater
deep?
levels change season to
Hmm.
season, right? And how deep the groundwater is too. So we installed 12 monitoring wells and 3 what you call piezometers. And a piezometer
Isometers.
is it's a way of being able to figure out what the water level is. So
I
we did
like
that. We
that word.
installed
But
3 of
Don,
those. Yep,
before we move any further ahead, I have a question. And so my
sure.
question is about how deep are these monitoring wells?
It just depends. It really depends, Jen, and on how far it is, how deep it is to get to the water table, what you call the water
Hmm.
table, right? And we're going to show a little graphic a little bit later on that shows where that water table is based on our wells. It's a good question, right? Because you drill the well until you start seeing basically water
Water. Hmm.
appear, and then you know you've tapped into the groundwater, right? You've tapped into that reserve of groundwater there. So it can vary quite a bit. Just like the subsurface can vary, right? It can be soil,
Hmm.
it can be rock in some cases, right? In some cases we have rock, and so the water gets in through the fractures, like the cracks in the rock, and
Hmm.
then can filter down and into like a reservoir kind of situation. Um, we measure the groundwater at different times of year. So in the summer, the
Yeah.
fall, and the spring. Obviously, in the winter, everything's frozen. It's hard to measure that when it's frozen, but that gives us an idea of what the how the system works, right? And how much of a change there is from season to season. We did that. So we did that in July 2020, October 2020, and May 2020 to understand seasonal fluctuations in groundwater. We took samples from the 12 monitoring wells. So we're taking these water samples and we're analyzing them for groundwater quality, right? And when we talk about quality, that basically means we take a sample, we send it to the lab, and we get an idea of what the characteristics of that water sample are. What's the chemical composition? What are the physical characteristics of the water? For example, like the temperature, pH, things like that. So we do a very detailed sort of analysis of those water samples because we need to understand what the water is like in the study area, and we do it at different locations because it can change depending on where you are because the geology is different. The things that affect the chemistry of the water, can change from place to place. So
Hmm.
um, each sample, I guess, as I said, will get tested for a wide range of chemical parameters, and we'll get into that. This next slide, what what I've got on here is just the groupings. So you've got different, when you send them to the lab, you can ask for different tests to be done. So you could say, I want general chemistry and inorganics. So inorganics would be chemicals that aren't hydrocarbons, that don't include carbon and hydrogen only. Um, there's nutrients, things like ammonia and phosphorus, things like that. There's metals like iron and lead and mercury, and then there's organic compounds which are hydrocarbons, right? So they consist only of carbon and hydrogen in them. And then we also test for radionuclides like radium 226 as well too. So these are so we send these samples off to the lab and we get all kinds of data back, and then we can try to get an understanding of what the chemistry is of this water in the different places, and then compare it to previous work as well. So lots of activities definitely involved on the field side, and then we do what you call in situ hydraulic conductivity testing. So
Okay, that
what does
sounds very
in situ
complex.
mean? It does, yes, it
Let's
does,
we'll
and it
start with
really isn't
that.
actually. Yeah, like in situ means like actually right on site, right? So we're
Okay.
we're we're doing so you're right there, you're at the well, and you're doing the actual measurements right there, not somewhere else, but in situ, right on site. So when we talk about hydraulic conductivity, what we're talking about here is so when we install a well, we one of the things we do is test for hydraulic conductivity. And what it means is hydraulic conductivity is a measurement of how easily a fluid such as water, which is what we're mainly concerned with here because we're talking about groundwater, moves through that spaces and like spaces between the particles, the soil particles, or the fractures in the rock, right? How does it move through?
Hmm.
How quickly does it move through? So the measurements are they're very small numbers, as we'll see later on. It's measured in meters per second. You're talking about small numbers here because it moves through relatively slowly,
Hmm.
but it's important to understand, right? Because um, there's there's things called when it comes to groundwater, there's things called um, recharge and discharge. Okay, so when you think of groundwater, when it
Okay.
rains, some of that water seeps into the ground, right? So the conductivity testing allows us to identify, okay, how fast can it seep into the ground and then become groundwater, right? How fast does it do that? And it changes depending on where you are, right? Because it depends on the soil type or the subsurface type. It could be rock as well too, right? So that's why we do that hydraulic conductivity testing, is to understand how quickly water moves through the ground, right? And so it's a measure of how porous it is, right? The soil is. So water would move more quickly through sand particles, coarse sand, than it would through clay, right? Because the particles
Hmm.
are bigger in coarse sand than the clay particles, right? So if they're bigger particles, there's more space between them. So there's more spaces, more places for the water to seep through. So that's basically
That's
the
great.
sort of the principle behind it, anyway. And why don't we talk a little bit now, Jen, about the preliminary results of the surveys, because
All right.
it's kind of interesting actually. And
Finding.
we installed we installed 12 wells, as I said, and this map, it's you may not be able to see super clearly, but in blue on the map, the blue circles are where the monitoring wells were installed. So needless to say, they're installed across the route, the route project, so we can understand, what the water levels are like in different areas. So in the muskeg areas and the east-west stretch, we installed wells to understand how the groundwater behaves there and how much it fluctuates from season to season. And then in the upland areas, the north-south parts of the road as well too. So now let's talk a little bit about the groundwater level measurements. And so what you see on your screen now is just a sample. And Jen, as I was talking to you earlier today about, the idea is we don't show all of the results in these presentations because we'd be here for hours going through all this.
Hmm.
But what we're trying to do, right, is take a snapshot of like taking a segment of the table that's actually in our report, and explain it so that people can understand it and follow it, and then they can look at the full document with the results in it later
Well, that's
on
right
and have an
because
idea of,
they can they can find the monitoring well and the corresponding the
yep,
number for the monitoring well, and then they can read through all of that information because it's nice to know because you said there was 12 monitoring wells.
that's right.
So it's nice to know,
Yep,
where they sit and then what the results of the groundwater is in those locations.
exactly right. So this table here, we're looking at the peatland areas. So we had 3 wells
Hmm.
installed through the peatland areas, right? So you'll see the well ID because we have to give it a name, and then we talk about the soil. So in that particular area, the soil is peat, basically, right? So it's decayed um, uh, vegetation. It's all decomposed and really. So it's basically the soil through which the groundwater enters. And then so what we have here is the minimum and the maximum groundwater levels, and they're the units that they use is meters, is MBGS, which
Hmm.
means meters below the ground surface. Um, so zero point 0.2 meters means 20 centimeters basically below the ground surface is where the
Which is just a
groundwater
little
flood.
less. Which is just a little less than those school rulers, remember?
Yeah,
Because those things are 30
yeah,
centimeters
that's
or
right.
even 1 foot. So just a little less than
That's
that.
right.
So if you want to use
It's
something to measure with.
and just to give everybody an idea, that's a very high water table, right? Very close to the
Hmm.
surface. In many other cases, it could be much further down, but obviously in these areas the groundwater level is really high because Muskeg, these are wet areas, right? Even in the
Hmm.
summer they're really wet. So and then if you see like a negative value for meters below ground surface, that means actually above, that means when they took the measurement the water was above the ground surface. So a negative zero point 0.2 means it was above the ground surface. So anyway, that's what that's what that table means. So you can, if you want, dive into the final report, and then it'll help you interpret and understand
Yeah.
these things.
And then it tells you, maybe you can help explain this part. So the seasonal
Sure.
variation for the slide that we're looking at for well ID,
Yep.
the first one. So it
Hmm.
said seasonal variation is zero point 0.2. So that's about, we just discussed the kind of the
20
length of a
centimeters.
ruler. So that would be about 20 centimeters difference between the
Yep.
minimum and the maximum. Am I correct? So do we know? Oh,
You
here we
got
have
it.
the minimum
That's
and the
exactly.
maximum.
That's it. So you just
Nice.
subtract the minimum from the maximum, and then you get the variation, right? How all it is
Excellent.
simple math between the two, and then you'll see on the other two wells
But I have
there was
another
no change
question.
whatsoever. Sure.
Yeah, I have another question. So the minimum and the maximum, do we know what seasons that was taken in?
I don't know. It could have been summer, spring, summer, or fall. I'm not sure. That's in the actual report,
Okay.
but it was likely the min. I'm just guessing, but I would likely the minimum would be in the fall. Typically, the water levels are lower, and
Mm-hmm.
the maximum would be in the
Yep.
spring, right? So you're probably looking at fall to spring for SPO1, and that's typical, right? Like spring, as we know, water levels are high, surface water levels are high, so are groundwater levels because there's so much water, right, from snow melt, etc. And that water, a lot of that water goes into the ground and raises the groundwater levels up, and then it raises the surface
Right.
water levels up too. So yeah, lots. But again, as you can see, lots of information in these tables.
Mm-hmm.
Then if we move to hydraulic conductivity, which just to remind everyone is a measurement of how easily like a fluid or water can flow through the subsurface, whether it's soil or rock. Um, so you look here at this table, we've got the well ID. Screen interval is another, I'll explain that another time, but that's a whole other thing. The soil or formation is the type of soil, right? That
Oh, I like
it's
that we can
traveling
see
through.
that. Mm-hmm.
Yeah, it's kind of interesting. And then the hydraulic conductivity is measured in meters per second. So if you look at these numbers, Jen, like you look at, these are small numbers, right? So for look at WQA1. So the hydraulic conductivity is 4.2 times 10 to the negative 6. So you got to move the decimal place 6 spots to the left. So it's moving very slowly
Okay. Yeah,
through
my brain does
that.
not math, so I sure appreciate
Yeah.
help with
Well,
learning this table.
so if you look at these numbers, Jen, so you see there's one that's 4.2 times 10 to the negative 6, and then the next row beneath it is 1 times 10 to the negative 7.
Right.
That's a smaller number, right? Because so it means it's even smaller than 10 to the,
So
so
does that
whatever time it means it, so if it's a smaller number, it moves even more slowly.
okay.
So if you look at WQA2, the water moves more slowly through silt and sand till than it does through granodiorite. I'm not a geologist, sorry about that. Um, so that's what that means. So you're talking about very slow movement, but it's still faster through the granodiorite, if you know what I mean. So anyway, the idea is to just give people an understanding. These numbers are very close to each other, right?
Mm-hmm.
You're talking about like 0.00000, one or like one hundred thousandth of a meter per second. You know what I mean? Like it's very slow, but it's still informative, right? It gives you an idea of how the water flows through there. And then if we move to the next slide, let's talk about the groundwater quality. So this big table here, I've only taken a snapshot of it, but in this table, on the left-hand side, we have what you call parameter. And when we talk about parameter, it's a measure. So we're looking at the measurement. Those are the different measurements. So you're measuring metals, right? In this particular case, you see total metals. And then you have aluminum, antimony, arsenic. These are all the different metals that we test for in the lab. And these are all chemical parameters. That's what you call them. And then as we move to the right, you'll see there's a column there called RDL, which is like a detection limit. So the machine that tests the water for aluminum, for example, its detection limit is 1. And then the units, concentration units, so how much of that chemical per volume of water exists. So all it is sort of to give you an idea of, okay, um, that's the detection limit. Like if you've got even less than that, then you won't even pick it up when you're testing the sample. And then you'll
But I
see
have.
you've got a sure. Yeah, go ahead.
Can I interrupt again? So
Of course,
before
absolutely.
we before we move on, I have a question. So how
Yep,
do we know that the nebe or the water is healthy? Is there a description that kind of indicates what the healthy makeup of water is? I know that's going to be pretty broad and pretty general, but
it is.
something that we
It's
could
a
see so that we can look at this
yep,
makeup and then kind of relatively determine, how healthy the water is, understanding that the chemical makeup of the water is going to be
yeah.
different all around the territory that's where there's testing, right?
hmm No, that's a great question. So you'll see the other two columns as you move further to the right: GCD, WQ, and OD, WQS. These are what you call guidelines, right? So these are things that we can compare to. And so again, every place is different, right? But these are the guidelines give us sort of an idea of, okay, what might be a concerning level, you know what I mean? Like a concentration of a chemical that's something we need to look at a little bit more deeply. So the
Hmm.
guidelines play that role, but you can't go by them strictly, right? Where you say, oh, okay, like if you see those gray shaded areas on the table, what that
Yes.
means is an exceedance. That's an exceedance of the guidelines because you see the first one
So it's a
is aluminum,
okay. So
right?
it's a bit
And we had
over. Okay.
122, and then the guidelines, the two different guidelines are 100, right? So what we do is we automatically flag these exceedances, and that starts to give us a clue. It doesn't tell us the water isn't clean, or it doesn't tell us that. I mean, it gives us something to look at. It's something that makes us dig in a little bit more deeply. But what we do is typically in that case is we'll look at previous work that's been done in the area, right? So we'll look at other water samples that were taken in the area, whether it's for other projects, whether they were mining projects or whatever, and we'll see what
Hmm.
results they got for the same chemical parameters. And, sometimes you'll run into cases like, for example, on reserve. Maybe if you were doing water sampling on reserve in certain areas, maybe in certain areas on reserve, where there might have been fuel storage tanks or something, maybe the groundwater in those areas, it might have higher levels of, petroleum hydrocarbons, right? Because
Hmm.
maybe there's gas in the soil, you know what I mean? Leaked
That's right,
fuel
and it
that's in the
continues
soil
to
that's
kind of
sitting in.
yeah.
So that's where you can. So again, you have to be like a detective if you're trying to sort of interpret all this stuff. You've got to look at these clues, and then you have to look at previous results, and you have to say, okay, is this is this is this likely contamination? You look at land use, right? Were there any industrial plants in this location? Obviously, in this case, that's not the case. These are This land is virtually untouched, right? But if you're in a more urban environment, you'd say, okay, was there any industrial use on this land? And you look for clues, right, to be able to identify whether it's actually contaminated, or sometimes the levels are just higher naturally, right?
Right.
And in our area, um, like if you look at the note on that slide, naturally elevated dissolved organic carbon, hardness, which is like hardness is a measure of the pH of the water, which is like
Hmm.
acidity of the water. So the more like it goes like 0 to 14 essentially, and so if it's above 7, it's considered what you call harder, or
Yes.
more basic. And then if it's under 7, it's considered more acidic. So in this region, you quite often can get elevated hardness of water. Iron levels are higher, manganese are higher as well too. Sometimes arsenic, sometimes too, because the underlying rock might release chemicals, and that's
Yes.
just the way it is, right? That's just the way
Yeah, and I've
the
heard
environment is.
that can be a natural
Yep,
substance.
yep, yeah, absolutely. So there's nothing that says, "Yep, that's contaminated." You have to follow the clues, and you have to try to interpret things, look at all different kinds of information, and sort of weigh it all and figure out. Sometimes you might pick something like that up, but in an area like this, which is basically untouched, undeveloped, you're not gonna run into things. You're running into when you're seeing elevated levels, it's likely just naturally occurring that way.
Hmm.
This next slide, this hydrogeological conceptual site model, may not be super easy to see in detail, but it kind of summarizes, everything that we did as part of this work. So if you look, what we're looking at here is like if you're following the road, you drive, you're basically cutting a slice through the road. So you're showing how the road changes in elevation. So on the left side, you're at a higher elevation. So elevation is the height of the land. And as you can
Hmm.
see, as you move further east on the road, you're dropping down in elevation. Now, not a lot. You're dropping down, I don't know, I can't even, I'll have to
Few
look at this a
meters.
little bit more. Yeah, it's not a lot. You're going from 200 meters, let's say roughly, to down to like 175. So you're talking a 25-meter drop over 107 kilometers roughly. So it's not a super steep area, but it's interesting, right? So you can see on here the different monitoring wells that were installed. You can see how deep they went. And so there's what you're seeing here is you're also seeing the values for hydraulic conductivity. That's the K values. Like you'll see it on the left hand side. Average K equals 5 times 10 to the negative 2 meters per second. So this sort of takes everything and puts it all together, and you see little blue arrows on the gray area. Those little blue arrows are indicating the direction of the groundwater flow. So in the western part of the road, it's draining towards Hudson Bay, and the eastern part of the road, it's draining more to the east towards James Bay. So
Okay.
it's kind of an interesting little graphic there, I'd say. But so that's the groundwater story, Jen. In a nutshell,
Excellent.
30-minute groundwater story. There's a lot there, but um, hopefully it was semi-understandable.
I think so.
So,
You've helped simplify some of the terms and how to analyze or look at that data, which is very important. Because
and if any of our,
I am no expert in any of that.
but if any of our viewers or listeners have questions about this,
Hmm.
I'm not a groundwater specialist either, but you can send us the questions that you may have, and we can, or we can talk to our experts and respond back to you in terms of some of the results that we got. So we're
That's right.
definitely open to that. So wow, that blew by, Jen. So that wraps up today's discussion, and we hope this was helpful. We hope it encourages you to join us again next week. And next week we're going to talk about geology, terrain, and soils preliminary findings. So we're going to talk
Oh,
about some of
excellent.
those boreholes that we drew to understand, that we drilled to understand, what the soil types are like in different areas. And don't forget to keep in touch with our project team members via the contact information available on our website, supplyroad.ca. And with that, miigwech, and we will talk to you again next week, right, Jen?
Oh, yes, miigwech and Balmapi.